Welcome, Shaler, to note video number 13. So in the chemistry unit, we have learned about how temperature and heat is an aspect of the speed of the molecules moving around. We have learned much about the periodic table and why it's laid out the way that it is and all of the properties of different elements. We have looked at the electron clouds to see how the valence electrons are what cause chemical reactions to occur, and we can use these to determine how many of each atom have to bond together to make a stable molecule with full outer shells. We are going to apply that now along with the law of conservation of mass, which says you can't create or destroy matter during a chemical reaction, to balancing chemical reactions. This is something that you have done multiple times already in the chemistry unit through different labs and whatnot, but let's actually take some notes on it and get some instruction. So a chemical reaction is always written this way. Whatever comes before the arrow are the reagents, whatever comes after the arrow are the products, and we don't say arrow when we say a chemical reaction, we say yields. So the reagents yield products. And you can think of this as a system, as we try to relate everything in science to systems. So we have our inputs, we have our process, and this creates the outputs. So it's always written as a what is called a closed system. So what we make in the end in the products or in our output can only be made from what we start with in our reagents. If it was an open system, then random things would appear, but that doesn't work with chemistry. We want to make sure that whatever we start with, we also finish with, so that we can abide by the law of the conservation of mass. So let's say this was our chemical reaction. Let's say we started with a triangle, a square, and a circle, and we're putting them all together to make something. So if you remember from the reaction-action lab, the triangle, square, and circle being put together, this would be an example of a synthesis reaction. And we might make a tri-squircle. It would be a triangle, square, and circle. And this is literally what's happening during a chemical reaction. We are starting with reagents, and we're putting things together to make products. And we're actually bonding the elements together to make molecules. So these would be 3 atoms. This would be 1 molecule. We use coefficients, just like in algebra, to balance the chemical reactions. So let's say a reaction was, again, the triangle, square, and circle, but it didn't make the shaped molecule that we saw in the previous reaction. Instead, it makes this molecule. Well, this doesn't add up to be this. We can't start with 1 triangle, 1 square, and 1 circle to make this. We need to start with multiples of these. And this is how we balance a chemical reaction. We have to make sure that whatever we start with, we finish with. So how many triangles would it take to make this molecule? Well, it would make 2. So we'd put a 2 in front of the triangle. How many squares does it take to make the molecule? Well, it takes 3. So there would have to be a 3 here, and then 2 circles. So the balanced chemical reaction would look like this. And then it would take 1, it would make 1. So if there's no coefficient listed, you can assume that it's 1, just like in chemistry. X is the same thing as 1x. All right, so here we have another chemical reaction. Now instead of just starting with atoms, we're actually starting with molecules. So here we would have a tri-square molecule and a double circle molecule. So this might be an example of a diatomic molecule like oxygen gas or hydrogen gas or nitrogen gas, where you would have O2, for example. And we're going to take these two and we're going to turn them into this. So we're going to end up with a circle with a triangle and a circle with a square. So in other words, this triangle is going to become part of that, the square is going to become part of that. This would be one of those other kinds of reactions that we talked about in the reaction-action lab. Well, is it balanced? Well, let's see. How many squares do we start with? 1. How many squares do we finish with? 1. We start with one triangle, we finish with one triangle. We start with two circles, we finish with two circles. So this is an example of a reaction that's already balanced. We don't need any coefficients because it would be like just putting a 1, a 1, a 1, and a 1. All right? We don't need to do that. It's assumed if there's no number there that it is a 1. All right, here's another one to try out. How would we balance this one? Well, let's see. We have one triangle to start, one triangle to finish, so the triangles are balanced. We have one square to start, two squares to finish, so the squares are out of balance. We have two circles to start, one circle to finish, so the circle is out of balance. There's no real right way to do this. You have to pick one, balance it, but that might cause other things to go out of balance, and then you go fix those, and then see what's out of balance and fix those, and you kind of just keep working at it until you get a system that works where you have equal amounts on both sides of the arrows. When we start talking about actual elements, there is, like I said, there's no real right way to do it, but there are recommendations sometimes for what kind of elements that you should start with and what kind of elements you should wait till the end, just based on patterns that show up as you get more experience in doing balancing chemical reactions. You'll start to pick up on some of these things. So in this case, let's just start with one. Let's say that we need two squares. We know we need two squares over here, so let's put a 2 here. So we need two of these squares. But that also means we're going to end up with two triangles to start with. Well, we need to make sure we finish with two triangles. So we need a 2 here for two triangles. Oh, and look what happened. Two circles matches up with our two circles. So by balancing the square on this side and making sure that the triangle matches with this side, we end up automatically balancing out the circles. So you just pick one and kind of start to go with it. All right, so here's a real chemical reaction, and this is one that you did in 7th grade. This is photosynthesis. You have already balanced this reaction. You learned how to balance this reaction in 7th grade. All of you did this. So if you don't remember, let's kind of work on it. Well, we have 1 carbon to start, but we have 6 carbons over here to finish. So that means we're going to need 6 carbon dioxides. Okay, solid. We have 2 hydrogens to start, but we finish with 12. So how many of these water molecules are we going to need to start with to have 12 hydrogens in the end? Well, again, 2 times what is 12? That's going to be 6. Well, then we can start to look at our oxygens. I would recommend that if there is an atom or an element that is found in more than one molecule, either in the beginning or the end, you save that one until last. So if we put a 6 here, and we put a 6 here, oh, I forgot to add this, my bad. Anything that is required to make the reaction happen, you write over top of the arrow. Photosynthesis cannot occur without light, so that light has to be there. Much like in the baking soda decomposition lab that we're doing in class, that's not going to decompose unless we have heat. That's why you wrote heat over the arrow every time. So if we put 6 carbons there, that matches up with our 6 over here. That also increases our total number of oxygens. We put 6 here for 6 water molecules. That matches up our hydrogens, but that's going to also tinker with the amount of oxygen that we have. So let's see what's going on now. So now we have a total on the beginning of 12 oxygen atoms in our 6 CO2 molecules. We have 6 oxygen atoms in our 6 water molecules. So 12 plus 6 is 18. So we have 18 water molecule or 18 oxygen atoms at the beginning of the reaction. How many oxygen atoms are we going to have at the end of the reaction? Well, we have 6 here. Oops, we have 6 here. How many oxygen molecules are we going to need to make up the difference? So if it is starting with 18, we need this to be a 12. So how many oxygen molecules do we need to get 12 oxygen atoms? Well, we would need 6. as you probably figured out already. The rest of these are going to be quick check problems. I want you to try to figure out how to balance these chemical reactions. Start with one, balance it, see how that impacts anything else, and just work forward. So we have this magnesium reacting with nitrogen gas. We have one of these double replacement reactions where we have cupric oxide and hydrochloric acid creating copper chloride and water. We have the classic volcano reaction. Whoa, hey, that just went away. That wasn't supposed to do that. The volcano reaction on the previous screen was baking soda and vinegar and what it makes. You can balance that one out. This is the one that you do when you grill. This is propane gas, and when you burn it, you combine it with oxygen gas, and you're giving off carbon dioxide and water. That's the reaction that happens in the burners down there. So, try to balance those. This last one is tough. You're going to really need to work at that one a little bit. But we have 12 questions in the clickers for booby trap number 13. You are probably going to need some practice and some work with balancing chemical reactions. So work at that. It's a process. Nobody does it automatically. You can't just look at a chemical reaction and say, oh, I know what it is. You have to work through the process. Also, remember, check out the link in the description of the video so that you can fill out the exit ticket. Have a fantastic day.